Yeah.
Dear friends, dear colleagues, good afternoon. And we can start this afternoon session with the first speaker, Nicola Petrov. Hi, Nicola. Nice to see you again, this time online.
Yeah,
Yes. Nicola is from the Astronomical Observatory Rogen, director, and he will give a talk about sun and solar activity, opportunities for observation and development. So Nick, please.
Thank you so much, and thank you so much for this invitation. It's a pleasure for me to be participant in whole Serbian astronomical conferences. That my monitor is visible, yeah?
Yes.
The presentation, okay. And maybe that one. Yeah. During the last few decades, we consider the connection between astronomy and the current issue of humanity.
Nicola, I'm sorry.
Yep.
I'm sorry to interrupt you. We cannot see your presentation.
Cannot?
Can you share, please?
Yes, of course. Let's try again.
Just please open in presenter mode, non-presenter mode. Sorry, just click and open it and then share.
Yep, like that.
Yes, great. It is here.
Perfect.
Great. Thank you.
I'm sorry. And connection between astronomy and the current issue of humanity related to the global climate changing on our planet. Some global changes in the Earth's climate are caused by a gravitational resonance created by giant planets in our solar system and the sun. The luminosity of the sun, the Earth's position in the solar system, and much more phenomena. These are factors that have both direct and indirect influence on the evolutionary processes on the Earth. Internal terrestrial dynamics, dynamics of the Earth's crust, geodal, static or gravitational and magnetic potential, climate dynamics, and all this impact on us like civilizations, and now is modern to make more and more observations and investigations about these processes and connections between the solar activity and the Earth like a planet, and especially the Earth climate. I want to say that observations and investigations of solar activity, they are very important, and for us especially at last. Of course, we want to understand and the solar physics and the space around us or beyond our galaxy. But on the other hand, we want to learn and present accurate physical models of the cosmic events that we observe is entirely related to studying the sun as a star. It closeness can reveal the physical processes receiving and transforming stellar energy in most detail compared to the other star. On the other hand, we are immersed in the postulated solar atmosphere, solar wind, life on Earth is primarily determined by the whims of the solar cycle. That defines the importance of further studies in the field of heliophysics. And at last, what means solar activity? This refers all phenomena observed in the solar atmosphere, especially solar atmosphere, like sunspots, active regions, prominences, flares, coronal mass ejections, um, and a lot of different events, including, of course, violent emission of eruptions and ejection from the sun. Especially, it's impossible to observe core radiative zone or convective zone like that, like a solar atmosphere. We say solar atmosphere, lower atmosphere. This is the photosphere or chromosphere, transition region between them, and of course, solar atmosphere. We means this solar corona. That solar corona between 1 and 5 solar radii from the center of the sun, and beyond these 5 solar radii, we call it this solar wind. Of course, there are still no sufficient answers to the questions related to apparent instability and periodicity of the solar magnetic field, the processes of solar corona, heating and the acceleration of the solar wind, the reason behind the solar flares, the processes of creation of the interplanetary matter, and in this case is very very important, and we have actual needs to make better observations and better models about all these processes that we can observe on the sun. Let's see now how to change. Okay, maybe the most important solar activities or solar activity processes. These are sunspots that the beginning of observations of them more than 400 years ago. Sunspots, they can exist in time between some minutes if they are very small, between 1,000 kilometers up to 5,000 or 10,000 kilometers. And of course, some sunspots, they can survive on the solar surface more than some months. If they are bigger than some hundreds of thousands of kilometers. The structure of sunspots, this is umbra and penumbra, that the temperature of center of the sunspots is less than 2,000 kelvins, that the surrounding of photosphere. And maybe counting of the sunspots present of us the most good known periodical active cycle of the sun, especially this is 11.2 years of a solar cycle. Now we are in the minimum of solar cycle, and maybe our colleagues started talking about this, that maybe this minimum of solar cycle now is the same like the last one, same minimum before 100 years ago. But over the last 2 decades, there is a serious progress regarding new possibilities and methods of solar observations and their physical interpretation. Nevertheless, the modern solar physics is still facing lots of answered questions, but finding the answers is directly bound to permanent monitoring of different manifestations of solar activity. There are, from one hand, ground-based possibilities of observations of some solar phenomena like activity, and on the other one hand, already is possible to have observations from the space, or these are space-based observations. The space-based observations here, I show only some few famous space telescopes like stereo, that there are two satellites, stereo A, stereo B. One of them already doesn't operate. The satellite SOHO, this is one very famous solar observatory that is in one position around the Earth on 1.5 million of kilometers from us. This is Lagrangian point that in every one moment is possible to observe the sun out from processes of our Earth atmosphere or clouds or something. And another one very famous observatory, we can say space observatory, this is Solar Dynamic Observatory, operated last some 10 years around. And all of you, maybe, I'm sure you know that we have another very special up-close solar satellites for observations of the sun, like a solar orbiter or a Parker solar probe, that the idea of them is to go so close to the sun and from first hand to observe the active processes in inner or closer solar corona, just beyond closed and beyond the chromosphere of the sun. Of course, ground-based of solar telescopes make possible to take a look at the sun in a large range of the electromagnetic spectrum too, visible or infrared light, radio waves, and yeah, I show only some telescopes of them, like Siberian Solar Radio Telescope in Irkutsk area, or maybe one of the most famous vacuum telescope for solar observations on MACMAT piers in United States, Arizona place. With these Earth-based telescopes and space-based telescopes observations, we combine them at last to prepare more and more exact results about physical processes that we want to understand in solar activity processes. And from space-based observations, generally we observe invisible light in ultraviolet, to say that is invisible from the surface, but wavelength like 304, 131 angstroms wavelength, that is possible to observe invisible from the Earth processes on the solar atmosphere. And at last, we start to understand more and more about magnetic reconnections in this solar corona close near solar corona to the sun, or what happens with heating of solar corona that from the surface of the sun with temperature close or near to 6,000 degree Kelvins. At last, we have more than tens of million of kelvins in solar corona. These processes of heating of solar corona, they're still open for us. But step by step, maybe we start to understand more about all of this. Solar activity, interactions of this of solar plasma with magnetic fields at last. Now, for this moment, just some hours ago, using especially space-based solar telescopes and spacecraft, we take some data about the situation around us. The sun is quiet, more or less. We have only one small active region without sunspots, but this is processing. This active region is a process of starting the new solar cycle, 25th, and maybe soon we'll see more and more activation of the sun with sunspots or eruptions or something. And now you can see that the geomagnetic activity, this KP index is very low. In this case, if someone feels not good, this is not because we have problems with the solar activity. In this case, we must be happy that the sun has no problems for that moment. From other hand, observations from Earth-based telescopes starting in last 10-15 years, with some telescopes positioning, for example, in this case, in La Palma Island in Canary Islands. And what is the main idea? With some different filters of observations, we can observe the same active regions and the same active processes on different level of solar atmosphere. In this case, if you observe with wavelet, call it G band or 1305 angstroms, it's possible to observe absolutely the lowest atmosphere of the sun. This is the granulation of photosphere, and what happens with and how positioning the sunspots on the surface. Later, this is the one, another one layer between the photosphere and homosphere transition one region. Above about 500 kilometers, or especially observations in H alpha light, that is possible to see what happens in atmosphere, that the temperatures start to increasing. This call it solar tomography of solar processing, and they are very important to prepare data about connections between all these processes in different levels of solar atmosphere. And they present to us, these observations present to us a better picture about all these physical processes that connecting magnetic fields and solar plasma, what happens above the sun. Higher and higher. what happens in Bulgaria? The solar observations in Bulgaria historically they started. It's exactly after the Turkish occupations in Bulgaria, after the establishment of the first high school in Bulgaria. Later, this is the first university in Bulgaria, Sofia University, in 1895 year. And after the beginning of working of this of the university in 1897, the first one professor of astronomy in Bulgaria, Professor Bachevarov, established the first one professional observatory in Bulgaria that now is positioned in Sofia, and this is Department of Astronomy in our university. And he and themselves students, they start firstly professional observations of sunspots exactly. Because this was the most easily for them, of course. And some images of these first sunspot observations from Bulgaria you can see here from some of student drawings, of course, of some students of Professor Bachevarov. But later, later. Yes, in 1964, the first research expedition of observations of total solar eclipse on February 15th was organized in Bulgaria. In this case, I want to say that total solar observations and observations of solar corona, they're important for us because it's exactly present the possibility to observe what happens in solar corona if we are out from the space. And in this case, solar eclipses, they're very important. In the very beginning of 1990, the foundations of modern observatory of solar physics were led in Bulgaria by Professor Vladimir Derbedjiev, who built solar tower in our observatory Rosen with one 15 centimeter refractor for white light observation of active processes of the sun. It was the first important step to the realization of the idea of our observational based in the Institute of Astronomy. As a result of event more efforts, a solar coronagraph was built in the solar tower on National Astronomical Observatory Rosen in 2015. And here you can see the solar coronagraph that is with diameter of the objective 150 millimeters. And for first time it was possible for us to observe solar prominences on the solar limb in light of H alpha. These are our first observations, and the monitoring of solar prominences presented us possibilities to make data about velocity, plasma velocity in quiescent prominences, in active prominences, eruptive prominences, and for our team was very important to have observational based in Bulgaria that is possible to produce our self-observational data. And now, last 1 year, was very, very important. And what I want to say now in this presentation is that we have another one for us, another one level of possibility for observations of solar activity. And this is brand new one telescope, 30 centimeters telescope. Cassegrain that has very narrow bandpass filter with 0.3 angstrom band on the around the center of H alpha line. And here you can see some images of our telescope that still now is not in Bulgaria. Now these images, they are prepared from our colleagues from Ukraine, that they optically preparing everything from this telescope for observations. And the telescope is equipped with one very sensitive one camera, grasshopper, that is possible to prepare images more than 30 frames per second. This is very important and more or less new idea for observations of the sun, that with this many frames per second is possible to prepare good quality of images, especially when we want to cutting the negative effect of atmospheric scintillations around us. And now you can see that this brand new telescope for us presents some very, very good quality of active processes that they're in solar chromosphere. And this is first our step with ideas to have another some telescopes like this one, smaller telescopes, but with good quality of imaging processing, and to build another maybe 2 or 3 telescopes in different wavelength of observations. That will be possible to continue with our idea to observe different layers of solar atmosphere and to connect the different solar activity processing. And the idea is to understand more and more physical parameters about what happens in this in these cases. They are important for us because more or less everything depending on the Earth, like global climate, and the sun is our laboratory to understand more about these processes like the sun as a star, and impact the solar activity processes impacting on the Earth climate at all. And this is that I wanted to present our steps for generated new ideas and new techniques for observations of solar activity that we will make in our observatory in Bulgaria. And thank you for your attention, of course.
Thank you, Nicola, very much. Thank you for this very interesting presentation. Nowadays, this problematic is very trendy and needs some multidisciplinary approach, not just astro, but geo and data science behind.
Sure. Yeah, absolutely.
So now we can start with just a few quick questions from the audience or from the chat. Is there any questions? I don't see anyone.
Yeah. Thank you so much again for this.
Thank you.
For this collaboration with you and for this perfect meeting.
Thank you. Thank you, Nicola. See you very soon.
See you.
So we can start with the next speaker, Oliver Vince, Senior Research Associate from the Astronomical Observatory Belgrade. He is expert in the field of observational astronomy, and he will give the talk about news and future plans in the development of the astronomical station Vidojarica. So Oliver, please, if you are ready.
Yes, I'm ready. But I am getting a message that I cannot start screen share while the other participant is sharing.
I think Nicola will now stop sharing.
Mm-hmm. Okay, so just to find my lecture, this is the one. And if I remember, I should go to slideshow presentation. Is it okay on your side?
Yes, excellent.
Okay. Hello to everyone. This is the title of the lecture. And at the beginning, a few notes. First of all, I thanks organizer for the invitation. And just to know, most of the lecture will be supported by the text to make it easier to follow the lecture online. And for the same reason, I made the lecture very simple with no videos, no animation and other fancy things. I hope everything will go well in this online lecture. So this is the structure of the outline of the lecture. I would like to mention the brief history of the astronomical station Vidojarica, to tell something about its current status and future plan. Regarding the history of our station, it began in 2003 when the station was established. From 2005 to 2010, two buildings were built. One is the dormitory, and the second one is the pavilion for the 60-centimeter telescope. And only in 2010, the 60-centimeter telescope was installed in the pavilion. And several years after that, we installed a warm room in the form of a container nearby the pavilion and connected all instruments in the pavilion and telescope with the personal computer and other devices. From 2010 to 2015, it is the era of Bellissima FP7 European regional project, and its main goal was to provide a 1.4 meter telescope for our station, and to be able to install just in time the telescope to our station. In 2015, we built a temporary pavilion. This one is the temporary pavilion. It's a very simple roll roof pavilion. And finally, in 2016, the telescope was installed in the pavilion, thereafter calibrated and used for photometry and other observational tasks. Right at the beginning, we knew that that one modern telescope deserves a modern pavilion. So from 2017 to 2018, we built a pavilion for the 1.4 meter telescope. This one in the middle of the picture. And finally, in 2018, we moved the telescope from the temporary pavilion to the new building. In 2019, because of major problems with the rotating dome of the pavilion for the 60-centimeter telescope, we moved the 60-centimeter telescope in the then empty temporary pavilion, and finally in 2020 we have installed the pavilion for the 40 centimeter telescope. So let's begin with the 1.4 meter telescope. Unofficially, we call this telescope Milankovic, and I attach here some basic parameters of the telescope. As I have mentioned, it was provided through Bellissima European Regional Project. It was bought from Astrosystem Austria company in Austria. As can be seen, it is alt-azimuth mount. Both mirrors, the primary and the secondary mirrors, are from Lomo company from St. Petersburg in Russia. The mount is supplied with direct drive motor, which in practice means that the telescope is fast, it's silent, it's precise, and run with less friction, consuming less power. And the telescope control system, that is all devices and electronics which are responsible to run the telescope, are inside the fork of the telescope, which again in the practice means that the telescope is quite compact, and more or less it resembles to a plug-in device. The telescope has 4 ports or station where we can attach instruments. There are 2 Nasmyth ports on the left and the right hand side of the telescope, and 2 so-called band Cassegrain ports on the bottom and the upper part of the telescope. So as I said, there are 2 Nasmyth ports on the left and right side of the telescope. Both ports are equipped with a derotator, which corrects images that we are taking from the sky for image rotation. Additionally, the left Nasmyth port is equipped with a focal reducer to be able to catch a larger part of the sky. And currently, there is a Andor Iconel CCD camera attached to the telescope, along with the Andor 9-position filter wheel and these filters, that is BV-RIL broadband filters and H-alpha continuum and sulfur 2 narrowband filters. The field of view with focal reducer, which is currently installed, is around 14 times 14 arc minutes, and the pixel scale is 0.39 arc seconds. And the equipment on this Nasmyth port is exclusively used for photometry, astrometry, and imaging. On the other side, on the right Nasmyth port, as I said, it's also equipped with the derotator. There is no additional optics in form of focal reducer or extender. But there is an instrument selector, this black device in the center of the telescope. This is actually a device that enables redirecting the light beam into 4 different ports. Currently, there are 2 CCD cameras installed on the instrument selector. One is the Andor Icon 897 fast response CCD camera, electromagnifying CCD camera, and the other one is SBIG camera, SBIG CCD camera. And currently, these 2 CCD cameras are used for lucky imaging, but there are, of course, plenty other interesting observational projects that can be performed with the fast response camera. Of course, the telescope is not on the meadow, but in the new building, as can be seen on this picture. And I attach here some major future plans for the Milankovitch telescope. The first one is full automatization of the telescope. This is a job which is already in the procedure. The second one is regarded to the multiple ports available on the telescope. So our interest is to provide more instruments and to make observations more versatile. There are several options. Of course, the favorite option is to provide imaging spectropolarimeter that is 3 instruments in one device. Plan B is to provide the spectropolarimeter that is 2 instruments in one device. And the third one is to provide either a spectrograph or a polarimeter. And the third major plan is the telescope robotization, that is to enable observation in a Q scheduling mode, taking into account observation conditions like relative position of the target to the moon, position of the target relative to the horizon, weather, and so on. So let's skip to the 60 centimeter telescope. Again, unofficially, we call it telescope Nedeljković. And again, I attach some basic parameters of this telescope. It was also provided from Astrosystem Austria company. It is a German equatorial mount, also with good quality LOMO mirrors, and currently it is equipped with FLI CCD camera and optic filter wheel with broadband BVRIL filters. The field of view is in this system is 15 times 15 arc minutes with pixel scale around 0.5, with the notation that there is a focal reducer available, 0.5 times focal reducer available, which means that we can double the field of view and pixel scale. And this telescope is also used for photometry, astrometry, and imaging. Here are some future plans for telescope Nedeljković. Lately, we had huge problems with the mount of the telescope. So we want to replace the mount with the new direct drive mount from ASA company. This job is also in the procedure. Unfortunately, there is a delay in delivery because of the unfortunate circumstances with the COVID pandemic. And another distant future plan is to return the telescope to the old 60 centimeter pavilion. I said distant future plan because the prerequisite is to replace the old custom-made dome with the new one. And this is a new event at Vidojevica that is the 60 centimeter telescope. Actually, the telescope is not a new one. It was provided in 2004. It is a mid 16-inch telescope. As you can see, it is in the temporary pavilion installed on the original tripod but it is not used currently. It is a Schmidt-Cassegrain optical system, and it will be set up as an equatorial system. And to be able to accomplish that, we provided a wedge from our Hungarian colleagues. The pavilion that you can see on these two pictures, it was provided from Scope Dome company, which is located in Poland. And the pavilion is 3 meters in diameter. There were different flavors of the 3-meter dome in this company, but we decided to buy a full automated version, which means that along with the rotating dome, all the necessary devices, electronics were delivered to be able to automate the dome and to synchronize with the mid telescope. Here are some nice pictures from the, let's say, young working action, can I say like that? And again, I attached some future plans for the telescope and the pavilion. So we have to finish setup of the pavilion. After delivery of the wedge, we have to adjust the wedge into the pavilion, then to work around the telescope installation, on the calibration of the telescope, on its automatization, and finally to introduce the telescope into regular observing procedure. Manpower, it's a rarely mentioned part of Vidojevica. I am sure that most of you are aware that we are very soon celebrating 20th birthday of Vidojevica, and of course there is a huge accumulation of equipment and infrastructure during this 20 year. I attach here some most important equipment on Vidojevica. So we have 3 telescopes, 3 pavilions along with warm rooms, 5 CCD cameras with 5 filter wheels, 5 independent instruments like all sky camera, meteor station, seeing camera, and so on, several personal computer, internet net, and so on and so on. So, and on the other side, the manpower is not so accumulated. In the meanwhile, we have only 1 manager, 2 telescope operators, and 1 janitor. So for the future, this is a must to do for the future, close future. First of all, we have to increase the number of technical operators. We can organize working in shifts, and by that we will automatically extend the current 15 observing nights per month. And the other major goal is to engage observatory maintenance staff, which means engaging at least 3 people. 1 for systematic maintenance of the telescope and instruments. The other is for mechanical maintenance and instrumental adaptation. And the third one for IT administration, web administration, and public relations. Just to draw your attention to our website, Vidojevica AOBRS. There you can find plenty of useful links, but I would like to draw your attention to the link telescope time allocation, where you can find all relevant information and rule books to be able to write a nice proposal for our telescopes. Here are some statistics regarding the observation projects. Currently, there are more than 20 observational projects per semester. There is a good trend for observational projects to participate in large international projects like WEPT, Gaia, LSST, and so on. Although there are no spectrometers and polarimeter, there are an increasing number of ideas how to use these two instruments, which is an additional motivation for us to provide spectrometer, polarimeter, or both in one device, as I have mentioned. And as I listed a few days ago, there are more than 18 publications in different scientific papers since 2010. And this is my short summary. Thank you for attention, and I am ready for questions if you have. Thank you.
Dear Oliver, thank you very much for the presentation and for the information and the current status and what are the next steps and plans about astronomical station Vidojevica. And now we have time for a few questions, if there are any questions. Any questions? I see a raised hand from Michael Bilek.
Yes.
Hi, Oliver. So thanks for this nice talk. It was nice to hear you after a long time. So I have to have at least one question. So when do you expect that the 40-centimeter telescope will be in operation?
Hello, Mikhail. I'm very glad to hear you. Well, it is very uncertain because of the current situation. Actually, all our plans regarding Vidojevica, including the 40-centimeter telescope, is in a huge delay. When I was presenting my abstract, I was counting that we will already install the telescope and have some nice first images from the telescope. But the only action around the 40-centimeter telescope was one gathering to be able to set up the pavilion. So other steps that I have presented in the lecture still to be done, and unfortunately I cannot easily predict when will the telescope go into the full function. Okay. But we are doing our best to decrease this time.
Okay, so thanks, and I wish you good luck with your efforts.
Thank you, thank you.
We have time for maybe one question, but if not, we can thank to the Oliver and
thank you.
Thank you, and go with the program. Next speaker is Ana Budragovic. According to the AOB site, she's a research associate, right?
Right.
And she is the expert in the observational astronomy, and she will give us the talk about testing performance of the Milankovitch telescope. So, Anna, please.
Hello.
Yes, you can start.
My screen. Do you see the screen I'm sharing? Do you hear me at least?
Yes, yes, everything is okay.
Can you see the screen, please? Confirm?
Everything is okay.
Okay, thank you. Okay, I'm sorry, I couldn't make it full screen. I don't know why, but okay, this is the best I could do. Okay, I would like to present some ongoing work that is quite new here and challenging. It's hunting a low surface brightness feature. Now, this work has been done in collaboration with several colleagues from France. Michal Bibilek being one of them. He's also going to give a talk at this conference presenting our latest work. I will more focus on the performance of the Milankovitch telescope when you want to image something that is really deep embedded in the noise. This requires a special observational technique called dithering, and meaning pointing telescope around the target large enough so that individual objects fall on different places on the CCD chip. In this way, when you average these individual frames, you end up with the sky itself, with the sky gradient that needs to be incorporated in the reduction of the data. You need to correct for this because going very deep needs the images to be really, really flat. Another thing that is important is the reduction of data, and I will talk more a bit later, but first I will show you the video I got permission to show from Peter van Dokkum, the leader of the Dragonfly project. He made the video of, a second, sorry, I cannot go to the next slide for some reason. Okay. There it is. No, sorry. You see the video of imaging the single stellar stream. It's the stream on the left of the galaxy NGC 5907. It's an E-shaped stream. But there is one image here taken from the Blackbird Observatory where you can see multiple frames. This inspired us to take the same image, the image of the same stream. And here is our image. So you see on the left clearly this stellar stream. It is a single stream. Why only the people from the Blackbird Observatory image several streams? We don't know. It might be that something went wrong in the reduction process. We'll never find out since they lost their FITS files, so nobody can reproduce that. To take this image, we needed to integrate for more than 7 hours and reached 3 sigma surface brightness limit of 28.4 in the G band. When we converted to the G band, we used L filter because it's the widest one. And it's ideal for a situation like this. Now, how did we do it? In the paper, you have also the link to the pipeline. It's on the GitLab. And it's in Python. You have also a link to the similar pipeline in IRAF. It's the second link here that I wrote. The point is there are 2 main steps. First, like I said, you need to create this, like I like to call it a super sky flat. This is the image of one of these flats. So you can create the one by median combining all the images that need to be normalized to their median values that you get from the images with the object mask, because you want to extract the sky itself. And then you correct each image to this background by subtracting it, but previously in the last formula here, quasi formula here, we multiply the super sky flat with the median of each image, because this is this unchangeable portion of the background, and it needs to be multiplied with the changeable portion, which is imprinted in the super sky flat. Okay, now when this is all done, how do we know how far, how deep did we go? We need to measure the surface brightness limit. There are two ways to measure it. One is you could find a galaxy in your image and simply measure its surface brightness profile up to some point furthest away and claim this to be your surface brightness limit. However, you won't always have a suitable galaxy, or it won't sit in the right place, because you see, when you use this method with offsetting the telescope, only the central part of the image is covered with the total exposure time you used. All other parts will be less exposed. So there is another method that has become a standard one, and we also use it. It's measuring sky noise itself in the image. You do this by placing, you see in the left image, this square arc, these square 10 arcsecond boxes. You put a dozen of them, and they have their own root mean square, their own, if you prefer, deviation, and these values have their own distribution that has its own spread. The mean value, you see it on the left, it doesn't need, of course, and isn't a Gaussian function, but I illustrated it with a Gaussian function for simplicity. It has its own mean value, which is the limit you've reached, and its own spread. Okay, now this is all given in, this is all a flux here. You need to convert it to magnitudes by performing photometric calibration. And you do this by cross-matching your image with some photometric catalog like SDSS or Pawn Stars. You infer slope and intercept from it. And then you simply convert these upper and lower limit to the magnitudes. Now, by simply taking the average, it is the last formula first term, you have your surface brightness limit, and the second term is the error. It's simply the spread. It's purely statistical error, or observational error would be, and is larger, but we're good with this. Okay. More about that just in a second, because I also wanted to show you, I measured the change of the point spread function across the chip. Maybe it will be interesting to someone. All these ellipses here are a bit enlarged, so it's a bit dramatic view so that you can easily see it, but they're true. So going each way from the center, we got these ugly ellipses that are simply the average shape of several stars in that part of our CCD. It's the problem we face because I guess we have the reducer, but there's nothing we can do about it. Or we can try some deconvolution or something like that. But okay, what I really wanted to show you, to go back to my main topic here, is the measurement of the limit compared to other famous all-sky surveys. All the points here you see in the color are the points I measured on several nights with different filters to see how good are we in Johnson filters and also in this ELF filter that we very often use. Of course, since it is the widest filter, the ELF filter here, in the shortest time, like I said, you will go deepest. But with the ELF filter, you can only say if something is there or not. If you want to measure some physical quantity, then the Johnson filters become very handy, at least B and V. Okay, these all points are measured, like I already said, there are 3 sigma surface brightness limits, and they are converted to the G band for the purpose of comparison. And I've overplotted the limits from the SDSS survey and Dark Energy Survey, or DES for short, and Beijing Arizona Sky Survey, or BAS for short. So, taking into account that the G filter would be somewhere in between B and V in terms of what you would really see in the image, then I can say that even in about 1 or 1.5 hours at most, we beat SDSS. Now for DES survey, we're good, BAS not that good. But it is comparable. Now you could think that when you look at these points from the L filter, that maybe they will rise more, but they don't. Because I've already mentioned that in the case of NGC 5907 galaxy, we imaged more than 7 hours and we got as deep as 28.4. So this point is actually on this graph, it just would be on the right side, but we cannot go beyond this. The question is why? Obviously, we have some great light loss somewhere, because you see all these telescopes like DESS and BUSS, they are meant to image low surface brightness features. They're all designed to have CCD cameras in the prime focus. We don't, so maybe this is the reason why. There are also some really exceptionally deep images that we cannot compare to, like SDSS Stripe 82 data, like CFHT deep survey, like Dragonfly project. They're all above 29. But still there are things that can be done with the instrumentation we have. Thank you. Hello, are you there?
Yes, thank you very much for this telescope performance presentation, and it is nice to have a telescope like that. So now we have time for a few questions. So I'm looking for raised hands, but there are no raised hands. Maybe you can, yes, colleague Bilek.
Yes, so hi Anna.
Hi Bilek.
Thanks for this nice talk. It is actually interesting, and I found most interesting what you said at the end. It's, if I understood well, it doesn't matter if you take the image, if you are exposing for 2.5 hours or any time longer, and there is this limit.
It seems to be, yeah. Well,
yeah,
maybe
it's really interesting. Yeah. So yes. So my suspicion is that it can have something to do with systematic errors, something like changing of the brightness of the sky during the night or something like this. I'm not sure what it is, but it is good that you have found that this limit exists, so we can try to overcome it, and yes, and do something about that.
Yes, yeah. I hope so too.
Yes. So I can't imagine that it would be something is blocking the light. I think that it will have to do something rather with some systematic errors, and we have to find a way to get rid of them.
Yeah, okay, that's
okay.
nice.
So that was my comment. This was just this one.
Okay.
So thanks.
Any other questions or comments? I see no raised hands. Maybe it is interesting to tell us what are the generally what are the next steps in that direction of your research or something.
Well, this is not a project that is defined to have some specific goal. We're more exploring what kind of, like I said, low surface brightness features like stellar streams, shells, and dwarfs and things, well, like that can be imaged, and what how can it be useful. It's a completely new area, and I expect a lot of well, I expect a lot of things to be yet discovered there. For example, Dragonfly team discovered ultra diffuse galaxies that are really faint. Also, they discover their massive disks around galaxies that we don't see. They are in the optical. They are as large as H1 disks. So they all lie in this faint. They're all very faint. You need to expose really long, and since time is very expensive with large telescopes, I expect these small telescopes like ours, and well, I mean, many people from all around the world are now coming into this area because we expect many surprises here. Okay. I don't know what. We are hunting in the dark.
Thank you very much. So we can thank to Anna for this very interesting presentation and go with the program. The next speaker is Stefan Cikota. Is Stefan ready?
Hello, yes, I'm ready. Can you hear me?
Yes, yes. Stefan Cikota is from the University of Electrical Engineering and Computing and expert in small solar system bodies. So he will give us a talk about determination of stellar radii by observing asteroid occultations. So,
Yes.
please.
Hello, everyone. I hope you can hear me well and that you can see my screen. So I'm Stefan Cikota. I'm a PhD student at University of Zagreb with an assistant position at Faculty of Electrical Engineering and Computing, obtaining my PhD in a few months. I'm going to present today how to measure stellar radii by observing asteroid occultations. So just for a very short introduction, I will give some data on the solar system. So except of Sun and our 8 planets, we have today about nearly 1 million discovered small solar system bodies. From that, about 550 objects are numbered. Those asteroids are mainly spread in 2 large belts, the main belt of asteroids with 98.5% of all discoveries, and the Kuiper belt of objects in the outer solar system with about 1,000 discovered objects until now, and expected 70,000 objects larger than 100 kilometers. Additionally to that, according to the new definition of International Astronomical Union, we have also 5 dwarf planets. Ceres, which is the only dwarf planet in the main belt, and Eris, Pluto, Makemake, and Haumea in the outer solar system. So when speaking of determining physical characteristics of small solar system objects, there are basically 2 methods. The first one is direct observations, which are done by large telescopes and spacecraft missions. And the second are indirect observations, basically astrometry and photometry. But in the last 10 years, also stellar occultations. So occultations allow us to estimate the object's size, shape, atmosphere, and other features with resolutions of a few kilometers, which is several orders of magnitude better than any resolution of any Earth-based method. On the right side, here is an example of the binary asteroid Antiope, shown with one of the largest telescopes, Keck, imaged with one of the largest telescopes at the Keck Observatory, and by the occultation method, where you can see nicely dissolved the both bodies of the binary system. So stellar occultations occur when the light from a star is blocked by an intervening body, like an asteroid, from reaching an observer. Those are in global short duration events, and we use them to determine physical characteristics of small solar system objects, actually by measuring the time of the duration of the occultation, which can be done by observers being put on the path of the shadow of the asteroid, like in the sketch in this slide. And they are also beloved by amateur astronomers because they can be observed with very inexpensive instruments. Stellar occultations are in general very rare events because they are very difficult to predict and observe because the ephemerides of asteroids, especially trans-Neptunian objects, are far more uncertain than their angular diameters. In this extreme example, I'm showing the trans-Neptunian object Eris in the outer solar system of a distance at 96 astronomical units, whose angular size is comparable to a tennis ball at a distance of 411 kilometers. So basically what we are trying to do is to try to predict if this tennis ball at a distance of 411 kilometers is going to transit over a star in the background. They are rare, but once observed, mostly they result with high impact publications like these examples, where I would like to point out the most recent examples of showing trans-Neptunian objects and centaurs with rings around, for example, Haumea, Chiraclo, and also Chiron. Basically, the main challenge in observing occultations is reaching high temporal resolution. And this can be achieved by using large aperture telescopes and very sensitive detectors. Lately, we are trying to use the MAGIC telescope located on the La Palma Island on the Roque de los Muchachos Observatory, which is actually an atmospheric gamma imaging Cherenkov telescope, but its camera is contained of Hamamatsu photomultipliers, where we are trying to use the central pixel of the MAGIC telescope, because the central pixel is designed for detection of millisecond duration optical pulses, like, for example, the Crab pulsar optical pulses. And here it is an interesting fact that achieving very high temporal resolutions can be used to measure also stellar radii by resolving the Fresnel diffraction fringes which are observed in stellar occultations. So now I'm shortly going to explain the basic idea of such observations. So you all may be familiar with the phenomena of diffraction, which is actually the interference of waves from a source when they encounter an obstruction. For example, when monochromatic light falls through a narrow slit in the distant screen, you will observe a diffraction pattern. It is a school example which we even can very nicely show through this formula for the condition of the minimums of the fringes. When observing asteroid occultations, the case is actually very similar. So in case of an intervening body, like an asteroid passing in front of a star, it also produces diffraction patterns. But in this case, it's slightly different because the light passes through a slit which has only one side or one edge on the side of the limb of the asteroid. And the result will be a diffraction pattern falling to the Earth's surface. And as the asteroid limb moves, the diffraction pattern glides across the ground together with the asteroid's shadow. To better understand what is exactly happening, we need to define some natural lengths. For example, here we are defining x, which is the distance from the edge of the geometric shadow of the asteroid's limb, d as distance from the asteroid to the Earth, and wavelength of light. Remember, at this stage, we are still looking just at a distant point light monochromatic source. With these parameters, we can define characteristic spacing between fringes on the Earth's surface by this formula. So square root of d multiplied by the wavelength of light. And the characteristic spacing on the distance of small solar system bodies in the main asteroid belt are going to be in order of a few hundred meters. For example, in this example with 400 nanometer light, the fringes, the characteristic spacing is going to be about 300 meters. And the intensity of the light falling to the Earth's surface in the transition area, we can calculate by this Fresnel integral, here shown in a complex type, and this complex integral can be also split into two real integrals. By plotting the relative intensity from the Fresnel integral in accordance to the distance from the edge of the geometric shadow, in the most simplest case of one single wavelength of 400 nanometers, you are going to get such plots where on the y-axis is shown the relative intensity, which is for a star 1. So this is the relative intensity of a star. And of course, during the occultation, it reaches nearly 0. Whence on the x-axis is shown the distance from the edge of the geometric shadow. So the asteroid's limb is approximately at 0 meters. Of course, stellar light is not monochromatic, it is polychromatic, which means that we must add together the diffraction patterns of each wavelength our detector is sensitive. For example, here are shown just 3 examples of 400, 500, and 600 nanometers wavelengths to show how is looking the Fresnel integral. And by using polychromatic light, which means by superposing wider spectral ranges in these examples between 325 and 375, or between 300 and 400 nanometers shown in red, we of course need to expect some cancellation in the fringes, which is nicely shown, for example, in this red polychromatic fringe. But it is important to note that in all cases, the first fringe is going to be significantly brighter than the nominal intensity of about 1. And this first maximum is normally going to reach about 1.4 times nominal intensity of the light source. Now we are going to shortly discuss what happens if you, instead of a point source, put a stellar disk as a light source. So now we are looking at a stellar disk of angular size theta, which projects into a circle of diameter d on the Earth's surface. And of course, the star's angular size will produce some effects in the diffraction fringes in comparison to the diffraction fringes of monochromatic light. In this example, for a distance of a small solar system body in the main belt of about 1.5 astronomical units and a star of a diameter of 1 milliarc second, this diameter on the Earth will be about 1090 meters. To understand the effect of the stellar disk to the fringes, we calculate a one-dimensional kernel. It can be done by breaking the stellar disk into slices. For example, this circle shows the stellar disk. The line in y direction shows the limb of the asteroid, and by breaking the disk in small slices, the one-dimensional kernel, like shown on the right side, must express the shape of the real intensity distribution of a stellar disk in accordance to the projection of the ground. And now, by convolving this one-dimensional kernel to the polychromatic fringes model, we are getting the final result, which are we actually going to observe, and it is going to be a slightly smoothened fringe pattern. For example, here are shown models of polychromatic sources with different disk sizes between 0.0 seconds and 0.7 arc seconds, and by which result by such fringes in a model. So by fitting the model to the observations, we can do conclusions on the stellar radii. And such observations have already been done, unfortunately not yet by the MAGIC collaboration, but by Veritas collaboration. And there is one disadvantage to such Cherenkov telescopes, and it is that the pixels of the Cherenkov telescopes cover a few arc minutes per pixel, which means that the background noise is very high, which means that even the most sensitive Cherenkov telescopes cannot observe stars fainter than 13th magnitude. And hereby I'm proposing, or I will try to propose also a collaboration with the Milankovitch telescope for such observations, because after we already have started a successfully collaboration with Professor Dragana Ilic in observing trans-Neptunian object occultations, this will give maybe more of very interesting results. It is important to know that by limiting the region of interests and using binned images, almost every CCD or CMOS camera can reach very high sampling frequencies between 150 and 200 Hertz, which is in general enough to detect such Fresnel fringes. Thanks for your attention, and if you have questions, I will be happy to answer. Also, if you are interested for any type of collaboration, just don't hesitate to write me an email.
Thank you very much for this interesting presentation, and thank you for the information about possible collaboration with Milankovitch telescope and other things. First, is there any questions online? If not, I would like to announce important information. I would like to ask you to stay online for a few minutes because we would like to take a conference photo together. So I ask moderator Dusan to prepare what is needed for this conference photo. Thank you.
Okay, thank you very much.
Thank you.
Vladimir, sorry, I think that Oliver has a question.
Okay, we have time, just announcement.
So just
Oliver.
Oliver.
I cannot see him. Is he maybe already? Yes, he's already in panelist status, so he can pose a question.
Okay.
Do you hear me?
Yes.
Yes.
Okay, I'm really not sure how to raise hands. I don't see any icon similar to hand on my Zoom. But okay. So Stefan, I have one question regarding to this collaboration. As you mentioned, you have already collaboration with Dragana,
yes.
In which I am also involved, as you know. And on the other hand, I have mentioned that on one of the ports of our telescope, there is a fast electromagnifying CCD camera.
Yes, I know.
And from our earlier discussion, I know from your comments and Jose's comments that it would be quite useful to try to make observation with this camera. So my question is, because the camera is directly attached to the telescope without any filter, is it important to make an observation in filter, or it's okay to make rough exposures?
So for our observations, which we have discussed in past, which was basically observing occultations of trans-Neptunian objects, we don't need any filters. But for specifically trying to observe diffraction patterns of stars with the goal to observe the stellar radii, it is not bad to have some filters just limiting the width of the spectral range. Because, for example, here in this example, in this diagram, you can see that as smaller the width of the spectral range is, so the cancellations of the fringes are getting smaller. In example of the red light, you can nicely see that just 2 or 3 first fringes are nicely visible, which is the range of 300 to 400 nanometer. If using a filter of bandwidth of 50 nanometers, for example, 325 to 370 nanometers, you will be able to observe 4 or 5 fringes. Of course, you can also, in case of no filters used, also nice result is giving just the intensity of the first fringe according to this relation. So to summarize my answer, it would be of benefit to have a filter, but it is not necessary.
Okay, thank you for clarification. Just to note that we are preparing our telescope either with fast response camera or if we fail with the other camera, Icon L camera, for the upcoming event on 23rd October.
I'm
So
looking forward to see.
So regarding this, just to know that we have no filter on the EM-CCD camera, and unfortunately we will not be able to go to our station to change the current situation. So it's encouraging that it is not necessary to have a filter. And
yes, for the TNO observation, no filters are needed. It's even better to have the full intensity and non-blocking filters.
Okay, thank you for answers.
Thank you.
Thank you, Stefan.